Welcome to this video. We're going to take a closer look at binding energy, and we're going to see another really excellent way of visualizing this concept of binding energy. Imagine I have three nucleons, so three protons and neutrons. The other way to imagine the three protons and neutrons is as if they're sitting at the top of a well, and that's what this is on the right. When I bring my three nucleons together, my protons and neutrons, I form an atom, and those nucleons drop down into the well. So the nucleus forms, and they fall into the well. We've learned that when the nucleus forms, there is a loss of potential energy, and that energy can't just be lost, it has to turn into some other form. It's converted into electromagnetic radiation, which we call light for short. So in this example, each of the nucleons, on average, gives off 4 mega electron volts. And when that light is lost, so is some mass, because mass and energy are equivalent. And on the right side, once my three nucleons fall down into the well, they've lost each 4 mega electron volts, so they get a little smaller, they lose some mass. Now, here's why this is such a useful analogy. The depth of the well indicates how much energy is lost per nucleon. Let's say we have 3. They form a nucleus, and each loses 4 mega electron volts, and because they lose electromagnetic radiation, because they lose that energy, they lose a little mass. But imagine we have a nucleus, which is made up not of 3, but of 4 protons and neutrons. When these form an atom, they fall into the well, but when we start with 4, they fall farther down into a deeper well. In other words, the depth of well represents the amount of energy which is lost per nucleon. So each of these gives off 7 mega electron volts because the well is deeper, and when they lose that energy, they lose a little bit of mass. So we could describe the depth of a well in terms of energy. This well is -4 mega electron volts deep, whereas this one is bigger, -7. Now, this is super useful because it doesn't just apply to the formation of an atom, but also to trying to separate an atom. Not only does it apply to the formation of a nucleus, but also to attempts to break apart, to separating a nucleus. So the correct term here is nucleus, not atom. Atom is too broad because it contains not just the nucleus, but also the electrons. And here we're only focusing on the nucleus. We don't care about the electrons circling on the outside. Okay, back to the video here. So I've got my nucleus formed on the left. If I want to break this nucleus apart, I have to put in as much energy as was given out. In other words, I have to knock free one of these by blasting it with about 7 mega electron volts on average, and then it pops off. So now I've separated one nucleus, and on average each nucleus would require I've separated one nucleon, and on average each nucleon in the nucleus would require 7 mega electron volts to be broken free. So what about the well? This is simple. To dig out of the well, to get down up to the top, you have to pop one of these things with 7 mega electron volts, and it comes out back to where it started. So here's an example. If we want, we could compare all of the different nuclei that exist in the world, in the universe, and we see that there's a certain limit to how deep the well gets. Some nuclei are not very deep. When atoms form, they only go to about they only lose about 1 mega electron volt per nucleon. Some atoms, when some nuclei form, they go deeper to about 4, so 4 mega electron volts is lost. Some are deeper still, and some are almost all the way down to -9. So the farther down we go, the harder it is to get out of the well. It takes more energy to get out of a lower well. So as we go farther down into deeper and deeper wells, we get more and more stable nuclei. Because it's harder to break those apart, it takes more energy. So here is our binding energy curve. The deepest that the wells can get is right here at iron, and the well is about 9 mega-electron volts deep. Right over here at hydrogen 2, the binding energy per nucleon is about 1 mega-electron volt. So you have to go down, you have to lose 1 mega-electron volt per nucleon to form that nucleus. Over here on the far right, the wells are about 7.5 mega-electron volts deep. So to form these nuclei, every single nucleon, every proton and neutron in that nucleus has to lose 7.5 mega-electron volts. So in each case, the well represents the binding energy per nucleon. It's how much energy each nucleon loses when the atom forms, and it's also how much energy you have to put back in to separate that and bring it out of the well, to separate a single nucleon and bring it out of the well. So as we go from here to over here, as we go to the right on the binding energy curve, the well gets deeper and deeper and deeper, and then it gets to about 9 mega-electron volts, and as we continue to the right, the well gets shallower and shallower and shallower to about -7.5 mega-electron volts. And this helps us see why iron is the most stable, because it has the deepest well, it has the largest value of binding energy per nucleon.